Hello everyone. So in this free lecture tutorial, we're going to discuss how gas temperature and gas volume relate to one another. And the gas law that helps us to understand the interrelationship between these variables is a law that we know as Charles's law. And in order to understand how temperature and volume of a gas relate to one another, we should draw upon common experience. Now, many of us have played with balloons as children, and so we have a lot of experience with them. And I'm not sure if it's something that you've actually tried before, but if you actually take a balloon and you make it cold, like in this picture down here, you'll notice that it looks like the balloon starts to deflate. Now, that's true even if you have a very tightly sealed balloon. And in reality, the balloon is not deflating. Basically, it is starting to shrink and shrivel up, but you still have the same amount of air in that balloon as you did when you blew it up in the first place. But nevertheless, it sort of looks like the balloon is losing volume and it starts to shrink. But if you go ahead and heat that balloon back up again, then it starts to expand again, as in the picture on the right. And what that does is it gives us some empirical evidence as to how it is that gas temperature and gas volume relate to one another. And if we think back to the kinetic molecular theory, the behavior that's shown in these pictures and the behavior that we would observe with our own eyes if we actually played around with changing the temperature of an inflated balloon should make some sense. Basically, if you recall, the temperature of a gas relates to the kinetic energy of gas particles. Okay, and we are aware that if we increase temperature, then a system of particles will actually start to move faster. The particles within this system will actually start to speed up and move faster as you raise the temperature. If you decrease the temperature, then basically what will happen is the kinetic energy of the particles will also decrease, and when the kinetic energy of the particles decreases, then the particles move slower. Now, the reason we should concern ourselves with how quickly or how slowly these particles are moving is, if you recall, basically, if I have faster motion, as in, say, the picture here on the right, then it's more likely that I'm going to get more particle collisions. Not just between the particles, but also with the boundaries of the container that contain the particles. So in this case, I'm going to get more collisions against the wall of the balloon. And if I have more particle collisions against the walls of the balloon, then basically that's going to trigger an expansion of the balloon. But if I have particles that move slower, as in the picture here on the left, then basically that means I'm going to get fewer collisions. And if I get fewer collisions, then basically I'm not going to get as many collisions against the interior of the balloon. And if that's the case, then basically there isn't going to be pressure pushing against the walls of the balloon to keep it at its current dimensions, and what's going to happen is I'm going to get a decrease in balloon volume. Or basically the balloon will shrink. Okay? And so what it does is it sets up this relationship that if I increase temperature, then the volume of the gas will increase. It's also true that if I decrease the temperature of the gas, then the volume of that same gas will decrease. So if you notice, basically both variables change in the same way together. This mathematically would actually be an example of directly proportional variables. And typically, if I have directly proportional variables, mathematically that translates into a linear equation. So, if that's true, then that means I should be able to write an equation of the form v is equal to some constant times t. Okay? If I rearrange and isolate the variables, then that means the volume divided by the temperature should equal some constant. So that means that for any set of gas volumes and temperatures, I should get the same number back again for a gas. And so this leads us to the most common form of Charles's law, which is this right here. If I have an initial volume V1 and an initial temperature V2, if I divide them, that should equal the final conditions, in which I have the volume of the gas under my final conditions divided by the temperature of the gas also under final conditions. Now, the important thing to keep in mind here, though, is you have to be in the proper units of temperature. Basically, you must be in Kelvin temperatures in order to have Charles's law work. And the reason for that is getting to that sort of boundary case where if I have the smallest gas volume possible, okay, in which case the particles are right on top of each other. Okay, that only occurs at the smallest possible temperature. And that smallest possible temperature is theoretically achieved at 0 Kelvin. Okay, so that's that boundary case of Charles's law that I was talking about. And so, since I have to have this be true, then every single use of Charles's law must involve Kelvin temperature. Okay, it's also important to realize that, again, we learned in the beginning of the chapter that basically there are 4 variables that control the state of a gas. And those 4 variables are volume, temperature, pressure, and the amount of gas. And this can be expressed in mass terms, or oftentimes it's also expressed in moles. Now, the important thing to keep in mind is all of these variables affect each other. And so, since I'm trying to isolate the relationship between volume and temperature alone, then whenever I'm considering a Charles's law problem, then basically I must hold the pressure and the amount of gas to be constant. And so Charles's law applies when pressure and the amount of gas are constant, and I'm going to allow volume and temperature to change. So let's take an example of how to use Charles's law mathematically. Suppose that I have the following example problem. It says on hot days, you may have noticed that potato chip bags seem to inflate even though they may not have been open. And so if I have a 250 milliliter bag at a temperature of 19 degrees Celsius and I leave it in my car, which has a temperature of 45 degrees Celsius, what will the new volume of the bag be? And so the way that I like to handle these problems, whether it's a Boyle's law problem or a Charles's law problem or any other gas law problem, is I like to organize my variables so that I know what information I have and what information it is that I'm trying to find. So as I read through the problem and I come upon the variables, so for example 250 milliliters, I should be thinking, okay, milliliters are units of volume, so this is a volume, okay? And so since it it's my original volume of my system, I will call this V1. When I have a 250 milliliter volume to this bag, basically the temperature at that same time was 19 degrees Celsius. So that should be my T1. Now, again, remember I said that my temperature units must be in Kelvin, and so the first thing that I should do is work on converting 19 degrees Celsius to Kelvin. Now, if you recall, to convert Celsius temperatures to Kelvin, I add 273. And if I do that, then basically I'm going to get 292 Kelvin. Okay? I'll be using that later. I'm going to continue to try and pick out my remaining variables. It says that my new temperature when I leave the bag in the car will be 45 degrees Celsius. So there's my T2. And again, I should immediately work on converting this to Kelvin. So 45 plus 273 should be 318 Kelvin. Okay, and I'm being asked for the new volume of the bag. So that's my V2, and my V2 is the variable that I'm looking for. So now I'm going to rewrite Charles's law. That's V1 over T1 is equal to V2 over T2. I'm trying to solve for V2. So what I'm going to do is I'm going to rearrange this equation so that I get an equation that reads V2 equals, and the rest of my variables on the other side. So if I do that, using some algebra, I should get that V2 is equal to V1 times T2 divided by T1. And so plugging in, that's 250 milliliters. My T2 was 318 Kelvin. And my T1 was 292 Kelvin. So I'm going to go ahead and run the calculation. So that's 250 times 318 divided by 292. And I end up getting 272 milliliters. Notice that my Kelvin units cancel. Now, let's examine this answer carefully. Basically, if I'm starting at 250 milliliters and I got 272 milliliters, then basically that means that my bag has expanded, or the gas within the bag has expanded. Okay, notice that I ended up getting this expansion when the temperature increased. Okay, now based on our discussion earlier in the tutorial, this should make sense that this should happen, because again, if I'm increasing my temperature, my gas particles should move more quickly. The more quickly my gas particles move, then the more collisions there will be, and the more collisions there are against the inner walls of the bag, then basically that should cause the bag to expand. And so I should have some confidence that this answer should be in the ballpark of the correct answer. So you should always re-examine your answers once you actually run the calculations. So go ahead and work on the follow-up assignment. And again, if there are any questions related to Charles's law or Boyle's law or any of the rest of the material that we've covered in Chapter 11, by all means feel free to email or bring up your questions in class. Have a good night.